So, have you ever wondered how an app goes from just a few users to, bam, a global sensation overnight? Well, today, we're going to pull back the curtain on the engineering magic that actually makes that happen. This is the story of the architecture of Scale. So, here's the plan. We're going to go on a build and scale journey. First, we'll look at that first huge decision every architect has to make. Then we'll dive into the chaos that comes with success. After that, we'll figure out how to direct all that digital traffic. And we'll even uncover the fundamental laws that govern these massive systems. We're going to peek inside a real-world giant to see how they do it. And then, to wrap it all up, I'll give you a kind of compass to help you navigate these big choices yourself. Okay, let's dive right in. Before anyone writes a single line of code, every single project, I don't care if it's a garage startup or a huge enterprise app, faces this one foundational choice. And you gotta get this right. I mean, get it right and you're golden. Get it wrong, well, you're pretty much building your dream house on sand. And here is that choice. It's the big one. Do you build a monolith, where your entire application is just one big unified system? Or do you go for microservices, where you're basically creating a collection of small, independent parts that all talk to each other? Think of it this way. Are you building one giant mansion or a village of specialized little workshops? The mansion is way simpler to start, but that village, that's designed for massive, massive growth. Now this is where it gets really interesting. This isn't just some theory from a textbook. We're looking at data from 67 real-world software architects, and it just lays the trade-off bare. I mean, look at this. On a 5-point scale, microservices absolutely crush it on scalability and maintainability. But, and this is a big but, look at that complexity score. The monolith is, without a doubt, the simpler, easier path right out of the gate. In this slide, it just perfectly illustrates the tipping point. The research is super clear. When your team is small, say under 10 people, a monolith just makes sense. It's the obvious winner. But watch what happens. The moment that team grows past about 25 developers, the complexity of having everyone work in the same big code base just becomes a nightmare. And that's when you see the preference totally flip, decisively, over to microservices. Okay, so let's keep going. You've made your choice, your app is a total hit, people love it, and that success brings a whole new and honestly a much better set of problems. And here it is, the moment every founder both dreams of and, let's be honest, kinda dreads. You are a victim of your own success. So many people are flooding in that your system is just buckling under the strain. Now, it's the best problem you can possibly have, right? But it's still a fire, and you have to put it out fast. So the answer is to scale. You've got to build more capacity to handle all that work. But it's not as simple as just flipping a switch. I mean, trying to keep things running smoothly while you're growing like crazy is one of the hardest challenges in all of engineering, and there are two very different ways to tackle it. So, option one, you can scale up. That just means making your one server bigger and beefier. More CPU, more RAM, the works. It's simple, but eventually you're going to hit a wall. There's a physical limit. Option two is to scale out. Instead of one big server, you add lots of smaller servers to share the load. Now, this is definitely more complex, but it's how you build systems that can truly handle millions and millions of users. So, scaling out, just adding more servers, that seems like the no-brainer solution, right? Well, not so fast, because the moment you have more than one server, you've just created a brand new problem that you have to solve. Think about it. You've got a dozen servers all ready to handle the traffic, but all your users are still trying to get in through the same single front door. So how do you decide where to send each person? This question introduces us to two pieces of tech that act like the traffic cops of the internet. First up is the load balancer. Its job is incredibly simple, but absolutely essential. It just sits there at the front door, and as every request comes in, it smartly distributes them across all of your healthy servers. This is what stops any one machine from getting totally slammed and keeps your whole application up and running. Then you've got the reverse proxy. If the load balancer is the traffic cop, the reverse proxy is like a super talented receptionist and security guard all rolled into one. It sits in front of everything. It shields your servers from being directly hit, it handles security, it caches common requests so they're super fast, and it does a bunch of other optimizations before the traffic even gets a chance to see the load balancer. Okay, so now our system is distributed. We've got lots of machines all working together in harmony. But this creates a new challenge, and it's a challenge so fundamental, it's basically a law of physics for software. It's called the cap theorem, And it's probably one of the most famous trade-offs in all of computer science. It's pretty simple, really. It gives you three things you really want for your system. But here's the catch. You can only pick two. You can never, ever have all three at the same time. It's just not possible. All right, let's break down these three choices. First up, we've got C for consistency. This one's simple. It means that everyone, everywhere, sees the exact same up-to-the-millisecond data. Think about your bank balance. It has to be perfectly consistent, right? Next is A for availability. This is just a simple promise that your system will always give you a response. When you try to use it, it's online, it's available, it works. And finally, P for partition tolerance. Now this one is huge. This is the ability for your system to keep on chugging, even when its different parts can't talk to each other because of a network failure. And believe me, on the internet, that happens all the time. So here's the choice you're forced to make. Because network failures are just a fact of life in distributed systems, you have to choose partition tolerance. You just have to. So that means your real choice is between consistency and availability. A bank, for instance, will always choose consistency. They'd rather go offline for an hour than tell you you have the wrong amount of money. But a social media app, they're going to choose availability every single time. Seeing a post from 2 minutes ago is way better than just seeing an error page. Okay, so let's see how all of these ideas, microservices, scaling out, load balancers, and that impossible cap theorem actually come together in one of the biggest, most complicated systems on the entire planet, Netflix. To even begin to understand how Netflix is built, you first have to try and wrap your head around its scale. And it's mind-boggling. It all starts with this one number, 250 million people using the service every single day. And when all those people sit down to watch something in the evening, that translates to 73 terabits of video data streaming out of their servers every single second. I mean, to put that into perspective for you, that's like downloading over 2,000 full-length HD movies every second. It's just insane. So how in the world do they manage that kind of load? Well, first, with thousands of microservices. This is absolutely key. It allows hundreds of different teams to work on different things, like your personalized recommendations versus your billing info, all at the same time without breaking the whole system. Next, they built their own global content delivery network called OpenConnect. They literally put their video servers inside internet providers' buildings to get the stream as physically close to your house as possible. For their data, they use different tools for different jobs. Some databases for perfect consistency on billing, and others built for massive scale for your viewing history. And the whole thing is stitched together by this huge custom caching layer that makes the entire experience feel totally instantaneous. All right, so we've seen the theory, we've looked at a real-world giant. Let's wrap this up with a practical tool that you can actually use to help navigate these choices for your own projects. So, how do you make this huge choice without just, guessing? Well, some researchers actually developed a formula to help out. It's called the Architecture Selection Index, or ASI for short. And it's actually a pretty clever way to turn all the stuff we've been talking about, your team size, your traffic spikes, how complex your app is, into a single data-driven score that points you in the right direction. And you can see here, it works beautifully. You take a startup with a small team and pretty stable traffic. They get an ASI score of 1.25. The recommendation? Stick with a monolith. But then you look at a company that's scaling up with a bigger team and really spiky traffic. Their score is 4.30. And the recommendation there is a strong go for microservices. A framework like this gives you a data-driven starting point, right? It replaces guesswork with a strategic compass. Because in the end, you're not just choosing between a monolith and microservices. You're really deciding what kind of future you're building for.